Welcome to P. Clark Calc, Practical Calculus for the Busy Math Student. And in this video we're going to take a look at how to calculate the area between two curves using definite integrals. So here we're looking at an application of the definite integral. It's finding the area between two curves on the plane. The definite integral itself always calculates the area beneath the function and above the x-axis, and if your function happened to go below the x-axis, it reflects that as a negative value, a negative or directed area. We can use that idea here by taking the region underneath f of x, which when we talk about f of x and g of x in this definition, there's kind of a slang that we use, the idea of the upper and the lower function. So you can't get too connected to the labels. But in our definition, whenever we talk about f of x, it's the upper curve. It's the one that has the higher y values over the interval that we're looking at there. So on our graph, the blue curve is the upper of the two over the region that we're trying to discuss here. And if we would just think about the region beneath that particular curve for a second, by the fundamental theorem, that would be the integral of f of x dx from a to b. Now what that would calculate is everything beneath the blue graph and above the x-axis. So it would be not only what's shaded on the actual graph, but also the additional shaded region here. Then if we subtract the lower curve, g of x in our definition is going to define the lower curve. And so when we take that integral, we're basically saying now we're going to take away any area that lies below that lower curve. So this region here lies beneath the lower curve, and so we throw that out. And so we see the net result is the original shaded region, what we're trying to calculate. The sum and difference rule states that if we wish to, we can go ahead and combine those into one integral, and we use that to state our definition, the integral of f of x minus g of x from a to b. A and b are the bounds of the integral. Should be pointed out, sometimes the bounds of the integral are explicitly stated. As we see here with a, it's just some value that is the lower bound. We're not quite sure why. And a lot of times the bound is the result of an intersection point. So you see here, the upper bound b is a place where the two curves cross. So sometimes we have to get in there and figure out where are these intersection points in order to define the bound. So ultimately what we're trying to do is build an integral here, and if we can find out what's the upper curve and call that f of x, and what's the lower curve and call that g of x, and what are the bounds of the integral, whether they're handed to us or we have to find them with intersection points, if we can write the integral, then we can go ahead and use the appropriate strategy to go ahead and find that area. So that's what area between curves is all about. So here in our example, we're looking for the area between the parabola y equals x squared plus 2x plus 1 and the line y equals 2x plus 5. And so we have the graph of that here, and the first thing you should probably notice is that the upper curve here is g of x and the lower curve is f of x. There's nothing magic about the letters here. We just have to keep that straight. So a lot of times I won't even say the name of the function. I just like to say the upper curve or the lower curve and just look at it. So the linear function g of x here is going to be our upper, and the parabola is our lower for the particular region that we're looking at here. Another thing is we don't know the intersection points. Now if you have your calculator and you're graphing, you can use your intersection finder. That can be pretty useful sometimes. If you don't, remember that intersection points are found by setting the two functions equal to each other. So in this case, we should be able to do it because it's a quadratic equation. This does not always produce a nice equation that can be solved analytically, but here we get x squared equals 4, so x is plus or minus 2. And so if those are unknown coming into it, if it asks for the region between the two curves, the implication here is it's bounded by these two intersection points. And so on my lower bound I have the point negative 2, 1. And then on the upper, here we have 0.29. So that should be enough to define this integral. So if we use our definition, we're going to find this area using the integral from negative 2 to 2 of the upper curve 2x plus 5 minus the lower curve, x squared plus 2x plus 1. And don't forget your differential in there. So at this point, you look at the integrals, and sometimes you may want to break it apart and treat it as two integrals, and the calculations be easier that way. In the case of polynomials, though, we can combine like terms, so it's definitely easier to simplify the integrand and then just do one integral here. So we end up here with negative x to the second plus 4. From negative 2 to 2. So then we can go ahead and apply the fundamental theorem here. Our antiderivative is negative 1/3 x to the third plus 4x from negative 2 to 2. And then we evaluate, so we end up with negative 8/3 plus 8 on the upper bound minus 8/3 minus 8 on the lower. So ultimately there we have 16 minus 16 over 3, which gives us a value of 32 over 3, or 10 2/3 as the total region between the two functions there. It should be pointed out that when you set up an area between curves problem, no matter where that region is, whether you're above or below the x-axis, that has to, by its definition, produce a positive result because it's upper minus the lower. If you ever do an area between curves problem and you come out with a negative number and you're pretty sure you did everything right, most likely you have the definition, your upper and your lower bounds reversed, and you just need to go back and flip those around, and that will get that negative sign out of there for you. So that's it. That's an important application of the definite integral, area between curves. Pretty simple, upper curve minus the lower curve over the bounds of the integral. If you found P-Clerk Calc helpful, you may want to subscribe to our channel, and if you'd like to learn more about calculus, you can find my textbooks here on Amazon for a really nice price. So until next time, I'm P. Clark.